Oops, closed tabs a little too aggressively there. Hi. We might as well just start. All right. Let me get some music going, some other music. And we'll get right into it. So, day 16 of Advent of Dreams, coming right up here. So far, everything has been going pretty well. Despite the problems getting harder, I have been improving, and problems are in general still just taking me about a couple hours of sort of real programming time to actually get, a working program. Some of that comes down to just learning Dreams better. Some of that comes down to building some tools for myself, learning some techniques, learning pitfalls. Honestly, a lot of it is just pitfall avoidance. So hopefully today will be no different. So let's jump into it. What is this name? This problem has a really baffling name. So let me pull up Advent of Dreams. Let me pull up Advent of Code here on my other screen. So, Proboscidea Volcanium. Okay. The sensors have led you to the origin of the distress signal, yet another handheld device, just like the one the elves gave you. However, you don't see any elves around. Instead, the device is surrounded by elephants. They must have gotten lost in these tunnels, and one of the elephants apparently figured out how to turn on the distress signal. The ground rumbles again, much stronger this time. What kind of cave is this exactly? You scan the cave with your handheld device. It reports mostly igneous rock. Some ash, pockets of pressurized gas, magma. This isn't just a cave, it's a volcano. You need to get the elephants out of here quickly. Your device estimates that you have 30 minutes before the volcano erupts, so you don't have time to go back out the way you came in. You scan the cave for other options and discover a network of pipes and pressure release valves. You aren't sure how such a system got into a volcano, but you don't have time to complain. Your device produces a report, your puzzle input, of each valve's flow rate if it were opened, in pressure per minute. Is that how flow rate works? Huh. And the tunnels you could use to move between the valves. Pressure per minute? That just feels so wild to me. Well, we'll roll with it. There's even a valve in the room you and the elephants are currently standing in, labeled AA. You estimate it will take you 1 minute to open a single valve and 1 minute to follow any tunnel from one valve to another. What is the most pressure you could release? Interesting. For example, suppose you had the following scan output. We've got a bunch of valves, A through J, with various flow rates. Each tunnel leads to a different valve. All the valves begin closed. You start at valve AA, but it must be damaged or jammed or something. Its flow rate is 0, so there's no point in opening it. However, you could spend 1 minute moving to valve BB and another minute opening it. Doing so would release pressure during the remaining 28 minutes at a flow rate of 13, a total eventual pressure release of 28 times 13. Then you could spend your 3rd minute moving to valve CC and your 4th minute opening it, providing an additional 26 minutes of eventual pressure release at a flow rate of 2, or 52 total pressure released by valve CC. Right. Because we open a valve and it releases pressure at a certain rate for the remaining amount of time, which gives us a total amount of pressure relieved. Sure, I guess that's why our pressure per minute stat makes sense. Making your way through the tunnels like this, you could probably open many or all of the valves by the time 30 minutes have elapsed. However, you'll need to release as much pressure as possible, so you'll need to be methodical. Instead, consider this approach. Right, and then we carefully choose which valves we open. Oh, this is wild. So we have an optimization problem. Oh gosh, I guess it was only a matter of time until an optimization problem cropped up, but this is gonna be difficult. All right, 1 second. I gotta grab my iPad and start drawing this out. This problem deserves a little bit more attention up front. Share the screen. Let's see here. And there we are. Got the iPad up. So, if we want to do this optimization problem, let's start by mapping out our actual scene here. So we've got A, B, C, D, E, F. I'm not laying these out in any particular way. I'm going to be moving them all around. Each of those has a flow rate, but what I'm curious about is that we have these tunnels that lead, like A leads to D, I and B, B leads to C and A. Are all the tunnels bidirectional? Because C leads to B, B leads to A, D leads to A, I leads to A. Okay, so I think I can pretty safely, I'll verify as I go, but I think that each of these is bidirectional, which would make sense. B leads to C and A, D leads to, or no, C leads to D and B. D leads to C, A, and E. We've already got C and A, but we need E. E leads to F and D. F leads to E and G. G leads to F and H. H leads to G only. I leads to A and J. Okay, so this was actually not too far off from kind of a sensible layout, you know, because I could like flip around to this to get a little bit more accurate picture, and I could move C up here. Whoop. Okay, so the sort of layout of this cave is a little more clear now. Maybe I'm gonna redraw some of these. Who needs the arrowheads? The arrowheads aren't helping anyone. Wait, I messed something up here. There was some... Yeah. I knew that I forgot one major line. I was like, they weren't all just literally a straight line. So, there we go. This is a more accurate picture. So, and this makes sense, I guess. So we, like, the path they're having me do that would be optimal is to actually move to valve D, open valve D first, move to valve C, move to valve B, open valve B, second, move to valve A, move to I, move to valve J, open J, move through I again up to A. This is convoluted. Move to D, move to E. Move to F. Oh dear. Move to G, move to H. Open that. How is this the most effective? Move to valve G then. So then we move to G, F, E, and open E. And then move to D and then to C again. Boy, this is actually super gross. Okay. And then we just wait it out. So this, I guess, is the thing that optimizes what they have shown me here. And let me actually go back to showing this so I can sort of show you what I'm working with here. The reason for this, I guess, the first thing they have me open is D because it has a high flow rate of 20. We then would move to C. No. Then we move to B, which has a higher flow rate, but is also on the way to J, which has a really high flow rate. And then we move all the way to H. I mean, ultimately we're trying, it's an optimization problem, right? Which, oh gosh. Okay. This is really, I'm not even sure how I would solve this with normal code, much less in Dreams. It's been a long time since I've done this style of problem. Oh gosh, gotta sneeze. So, I could certainly, like, brute force it. If I were doing this in a real programming language, I would brute force it. Or I could brute force it. Granted, that would be really gnarly for the level of input that they actually give me. You know, this would be a relatively large graph. And if I were to brute force like every path through the graph, that would be really, really computationally expensive. I think, let's see. What does it look like to just solve this problem in general? My hunch here is that if we think about this graph, you know, if I undo the whole roundabout path they took me through it, maybe I should write down the flow rates for each of these just so that we have an idea of values that we're working with. So 0, 13, 2, 20, 3, 0, 0, 22, 0, and 21. So it occurs to me excuse me a moment. This may be sort of a knapsack type of problem. And I may have to refresh my memory on how to efficiently solve knapsack problems. Or maybe just how to inefficiently solve knapsack problems. But the reason that I think it's sort of a knapsack problem is that, like, each of these, you know, if we consider starting here at A, imagine that we are just at position A. Each of these nodes here in our little cave system has like an expected, or like it has a total value if we go there now and turn it on, right? Because the example that they gave was well, here, I just want to like double check my math on this, but the example that they give is that if you move to valve D, or where did they talk about this? Yeah, so you could move to valve B and open it, right? Those are the two things you do. Each thing takes 1 minute. And so you have 30 minutes total. You move to valve B and open it. That means that from there on out, you have 28 times 13 equals, what did they say in the problem? 364 units of pressure relieved. And that's what we're trying to maximize cumulatively over the course of the whole problem. So so that basically makes me think that, like, you know, you could compute this for each node, right? Like from A, with this much time left, we have a value of 364 potential pressure from that. If we compute that for the other nodes, you know, C would be 28 times 2, or 56. J would be 21 times 8, or 21 times 28, which I'm not going to do in my head. I don't like doing things in my head. Oh, good work, Windows. 588. I'm skipping the ones that are 0, obviously. 560 for D. $84. Oh, except that this one is. No, this isn't. I've been computing these wrong anyway. They're 2 steps away, so the actual calculation changes. So this is part of it, right? Is that, like, I would spend it going to J, I would do like 1 minute spent, 2 minutes spent, 3 minutes spent opening it, which means that I only have 27 minutes left for the actual thing. So that would be 27 times 21, or, oh my goodness, like Windows, like really Windows? Search for 21 times 27, and what do you, wait, why did it work that time? It gave me, did I do 27 times 21? Yeah. It just does a Bing search and is like, what is an equivalent fraction for this? Coolconversion.com. Get out of here with that. Freaking ridiculous. What is the purpose of having a calculator thing if math expressions don't, like, reliably actually parse as math expressions? 567 for that. For E, that is 3 times 27, or 81. Could have maybe done that one in my head. This one is, let's see, 1, 2, 3, 4, 5, 6 minutes spent going over to H, which means that it would be 24 times 22, or 528 total pressure relieved. So, oh no, I need to do C as well. So that's just 2 times 27, 54. So each of these nodes in the graph has this kind of potential pressure relief right now. Now, unfortunately, it's not as simple as just going to whichever one gets you the most pressure and then, and then repeating the process, because each of these I mean, you can see, for example, that the problem that they, like the path that they recommend opens D first, despite it having a smaller total pressure relief than this one. But the catch is that you can actually get B open more quickly as a result, I think. So unfortunately, being that it's an optimization problem, you have to consider this holistic process of, like, you may have to do something that is locally worse in order to do something that is globally better by, like... On the other hand, I don't really understand why... I don't really understand exactly why this is the best way through this. I sort of would have expected, I mean, I guess, yeah, so this is 1 step away, whereas this is 2 steps away, and I guess that's probably kind of the dominating factor here, right at the beginning. But I'm just sort of trying to think, like, why wouldn't I go here first before coming back up here and then going down here or some such? You know? Okay, well, I mean, I believe it, but let me maybe step forward again then, do sort of another iteration of the problem as I currently see it. Your valve options here, excluding the 0 valves, are let's see, we've got B, C, D, E, H, and J. These are all the ones that actually have any kind of value. Their values right at the start of the problem are 364, 54, 560, 81, 528, and 567. Now, I'll humor them and go one more step of the problem over to D. So we've gone to D, we've opened that valve, so we will get the full 560 by the end of the problem. Now we could compute new numbers for all of these nodes based on their distance away and the fact that we only have 28 left. So B, for example, is 2 moves away, which means we would have 26 cycles at 13 pressure per, or 26 minutes at 13 pressure per minute, which 338 would be our new number for B. C is 1 step away, so it would be 27. Yeah, times merely 2, so 54 again. J is 3 steps away now, so we would have only 25 minutes. No, yeah. I summed this up wrong, didn't I? I forgot about the minute that you spent opening it. Psi, let's repeat this. So B is 2 steps away. That takes us from 28 down to 26. But then we have to open it, so that's 25. So it's 25 times 13. 325. C is only 1 step away. That's the minimum distance to it. So that would take us, the result would be 26. So it would be 26 times 2, or 52. J is 3 steps away, plus opening it, which puts us at 24 times 21, or 504. E is 1 step away, so that's going to be 26 times 3. And then H is 4 steps away, plus opening it. That takes us to 23 times 22, which is 506. So that is our next iteration of the problem. B, C, D no longer exists. E, H, J, and those have 325. Here, I'll like do this to indicate that this is the D case. 52, 78, 506, and 504. And so this process could continue, right, where for each step that each process that you could take, you would sort of, you then might pick C next, and then you would have B, E, H, and J left. And then you might pick E. I mean, I'm completely spitballing here. And then you might have just B, H, and J left. And so you could sort of go down this whole stack, like walk the thing in some order, and you would get a sum of values at the end. And the order that you go results in like a completely different stack every step of the way. But it means that the whole problem can be seen as a traversal through, like, you have B, C, D, E, H, J. From there, you can take one of 6 possible paths out of here, right, where you eliminate one. And so then you have 5 things, and then from there you have, there's 5 ways out of that. And then each of those is 4. So how many total paths are there through this? If you wanted to compare every possible way through the graph, I guess, let's see. There are 6 options at this level, right? Like six choices made here. 6 times 5 choices made here. 6 times, 6 times 5 times 4 choices made here. All the way down to just 1. I'm not sure. This equation feels a little familiar to me, but I can't place it. Does this help? I have found a pattern. Does this help? Yeah, I don't think that this helps. This did not help me get a nice closed form version of this thing that I was typing up. So, you know, whatever. This has this really nasty factorial looking effect to it. Did I do the math right? Because I basically think it is like, you know, from here. World premiere. But I mean, I think that I'm right, because I think that the pattern through here checks out, right? Tree 3, what is that? I'm so stupid. Ha! I'm overthinking this so hard. First of all, I was adding these up, but I absolutely should not have been adding them up, because this down here completely reflects the entire path through, right? It's like, you know, there were 6 options at the top, and then 5 options here, and then 4. And I just now realized, because it's factorial, because this is obviously 6 factorial, that this is literally just asking, like, you know, which way you go through this is literally identical to doing the number of permutations of this, because you're literally just asking what order do you go through these in, right? Like, that's literally the question. I'm drawing it out as this crazy tree when it's literally just what order are you going to visit these in and how many ways can you do that? Well, that's exactly frick. That's exactly what that tells you, right? So there's 6 factorial ways of doing this particular one. Now, unfortunately, 6 factorial is, oh, come on. Give me that scientific. Do you have factorial on your scientific calculator? No, you do not. Programmer calculator. Still can't do factorial. Actually. $720 possibilities. 720 ways that you could go through this. Now, to a computer, that's chump change. To dreams, where I have timers on everything, that's not so much chump change. Now, also, there are better ways of doing optimization problems usually than brute forcing. Because, you know, if we apply this logic to the actual problem they gave me, where, you know, we take a look and see that we have how many lines of input here? 50, right? Well, unfortunately, I'm sorry to report that 50 factorial is incredibly large. Absolutely not brute forceable. So, this is no good. It's no good at all. We really need a more computationally efficient way of solving this problem. Now, oh, that's not the same thing. Oh, it's been so long since I actually did, like, mathematically difficult programming problems. A grid ABCDEFJ versus ABCDEFJ on top and side columns. What would that do for me exactly? I mean, that would... The problem is that the numbers and the amount that you can get out of the problem sort of changes as you move around the graph. Right? Because you've spent a certain amount of time getting there, and it takes a different number of steps to get to wherever you're going for, like, the next step of it. So, what I guess I should ask, what numbers would I put on the grid? Is it time for me to learn what dynamic programming is again? It's been years. I might have to switch this over to the programming category instead of the dreams category and solve this in JavaScript before I solve it in dreams. Useless. Wikipedia is useless. Just utterly useless. I feel like I need to understand this bit right here. So this problem does feel knapsacky to me, although, like I said, I haven't done problems like this in a while. What? What's W here? Cap W? Did you even define what cap W is? Did you even define what it is? Maximum weight capacity. Sure. Okay. Okay. So what they're saying here. So the knapsack problem, I should clarify, is the problem of fitting. If you have a bunch of objects with a certain weight and a certain value, and you want to load up your knapsack with as much value as possible, how do you pick the optimal set of items? Because an object's weight is not necessarily correlated to its value, right? And it's not like you can just start by taking the most valuable thing and then the next most valuable thing and then the next most valuable thing until you're done. Because it may be that like a bunch of less valuable but much less heavy items end up being more valuable in total than just starting with the single most valuable thing and going from there. To start with the single most valuable thing and go from there is what's called a greedy algorithm, and it doesn't work in general. So now what they're saying here is that you can make a table where you like have if you have 4 items here and a capacity of up to 6, then you can just sort of loop through and let's see here. Right. Because you can bank on the recursive definition of the problem, you can look at previously computed results to move ahead in your computation. So like, okay, iPad time again. Let's just try to work through the example, whoops, that Wikipedia is doing here. And refresh our memory on how knapsack problems work. So, we have the following items. We have one with value 5 and weight 4, value 4 and weight 3, value 3 and weight 2, value 2 and weight 1. We then make a table here where we have up here the total knapsack weight. Oh, and then I guess the total weight that we can carry is 6. And so here we have the weight, and here we have the number of items. And then you can start to break it down where it's like if we have 0 items, we can have 0, 1, 2, 3, 4. We can have 0, 1, 2, 3, 4. What am I trying to say? 0 through 4 items in our knapsack, right? Because there are 4 items to choose from in general. Likewise, we can have weights anywhere from 0 through 6 in the knapsack. Now, the first columns shake out trivially, where if you can put 0 items in the knapsack, then obviously the maximum value of anything that you can store is 0. Likewise, since everything has weight, if you want to have 0 weight in your knapsack, then you're going to have 0 value. So those columns shake out trivially. Now, if you can only have 1 item, well then, let's see, this, how does this follow? They're doing this example here of like, oh, that's right. That's right. So the way that you can do this now is you can say for each item in your list, you can say now, what if I included this item in my knapsack? Because we're on the 1 item case here, right? So this really works out pretty straightforwardly. We only have to look at 4 different things to figure out the maximum value that we can store if we want a weight of 1. Well, except I'm confused because I'm thinking that I would get a different result from what they have in the table here. So what gives? I think that I would have 2 here, because I can have 1 item with a weight of 1 and a value of 2. But they do not get that. How do they not get that? What? 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 Boy, I don't know how anything works anymore. What do they get as their final answer? Useless. Just utterly useless. Like, Wikipedia, how can you be so useless? How can you, like, put all this effort into, like, making visualizations for these things, animations of stuff running, and at the end you don't even say what the answer is? Like, come on! You're just like, oh, here's a bunch of blinky lights, hope this helps. You don't even tell me what the answer to your example problem is. Like, come on! How can you be this bad at explaining things? This is so stupid. Unreal. And now here I am on just Garbage Geeks for Geeks tutorial site. Screw it. I'm going to go ahead with my own idea of how this problem works. So what I'm thinking is that at this point, if you're asking what is the maximum that you can get with weight 1 in one item, well, that's 2, because you would use this item, right? You would step through all 4 of these and go, that doesn't fit, that doesn't fit, that doesn't fit, that fits. So our maximum value is 2. For number of items, if you want one item with a value of 2, then you would get a maximum value of 3. Likewise up to 4, 5, and then these would both be 5 because there is no heavier item that could take advantage of the space, right? If you want one item in your knapsack and you have a total space of 6, then 5 is the best value you can get. Now, here's the fun thing. Let's consider what happens if we want 2 items in our knapsack and we want it to have a weight of 1. Well, that literally can't happen. I wonder here. Let me start with one that I know is possible. The 3 case over here. What would go here? You know, in this box. My thinking here is that you can iterate through each item and go like, for this item, say that we put this item in our knapsack. No, this doesn't solve it, does it? No. Because the previous values might include that item again. I was thinking we could do this cool recursive thing. The grid spots after selected modified the surrounding values for the next selection. Maybe. What I was thinking would happen here is that, like, if you were to go here, say that you picked this item. It's got a weight of, well, that one has a weight of 4, so it wouldn't work anyway. You can't include that and do the rest. But say that you did this one, right? Say that you included this item in the problem. Well, now that item would have, it has a weight of 1 and a value of 2. So we're up to 2. But we've used up just 1. And so then we could say now that we've used up 1 of our weight, we're actually looking at weight of 2, remaining weight of 2, and 1 more item. And what's the most value you can have there? Well, 3. So then your total value would be 5. So you can see how there's sort of the recursive definition to it, where I like, you know, if I'm here and I calculate some value, and then I know how much space was taken up, I can just look back at a previous value and go, well, I already computed the maximum the maximum value that I could get for that reduced weight and that reduced number of items. I guess it would be, you know, somewhere along this row, because there's 1 fewer item and some reduced weight. So one of these 4 items. But this doesn't actually work for me because it doesn't keep track of, you know, I could end up using one of these more than once. Okay, so I'm sorry, I gotta go through this pseudocode. Oh, I still have my iPad in the way. So for the 0-1 knapsack problem, which is where we can have only, I mean, that's basically the one we're dealing with, where you can't have more than 1 of the same type of item in your knapsack. So for J from 0 to W, we're going to be building up this table here. So J goes from 0 to W. So in our example, it would be 0, 1, 2, 3, 4, 5, 6. 0 through 6 total weight capacity. For I, that's the number of items. So that would go from 1, 2, 3, 4. Then they're saying we do zero this out, so it's going to be like the I equals 0 column. Oh, there is supposed to be a 0 here. Neat. No. So annoying. There we go. So they're basically just showing that zero out process, which does make sense to me. And to be clear, I should really label these items. This is the like weight of the knapsack, and this is the number of items. And then they say for I from 1 to N, and then within that, J from 0 to W, which basically means we're going to go through the rows in this order. Pretty straightforward. Just like they were showing. I'm not doing, oh my goodness. I wasn't showing the iPad. This is the table we're doing, right? So we're sort of showing the same thing again, and we're going to be filling out the table in this direction. The 0 rows hopefully all still make sense because, again, 0 weight means you can't include any items. 0 items means you can't have any value, or there's no weight, you know, so it all zeroes out. Now, they say, let me, let's see, how can I put, beautiful, perfect. So they say, if the weight of item, this isn't the number of items, this is the item. This is the item that I am actually looking at. So let's pull back in this. Tell you what. We'll just erase all this because it was wrong, and we're now going through the correct process per the pseudocode that they have listed. So they say basically if the weight of this item, so this is not, I gotta label things a little bit better here and get some helpful data out in place. So this is the item. Item 0 is sort of like a pseudo item. It kind of doesn't really exist, but we can have it in our table just for the heck of it. So these items have weight 4, 3, 2, 1, right? So if the weight, they say the logic goes like if the weight of if the weight of the item is greater than the total weight that we are looking at right now. So to be clear, we're going like, if this is our weight, we're currently looking at weight 1 right now, and item 1. That's where our loop is at. If weight of I, in other words 4, is greater than j, in other words 1, that's basically saying this item does not fit in the knapsack. The weight of this item exceeds the capacity that we are currently going for. So if that's the case, then we're going to fill in this grid space with the previous item. So that would be like 1 space up. So that would be 0. That continues for this, right? We can see that the same principle applies to all of these, so that, you know, because this thing has a weight of 4, you know, these all fill in exactly the same way. Here, I gotta draw this out a little nicer. And then at this point, 4 does go into the grid correctly because now, hey, it fits. And so we say it is the max of which spaces? This space, which basically represents, so like the m of I minus 1j is basically like the max, or it's the maximum value we could get with the previous item. We also look at I minus 1 and then j minus the width of the item, right, which is basically like the, you know, since this item has a weight of 4, then that would be, you know, okay, what's the maximum knapsack value we could get with this item already in there? We added it to the knapsack. That means that we have 4 minus 4, or 0 units of weight left, and so we would look that up in our table. Except, wow, this is such confusingly done code. Such poor example code, because here's the thing. This line if we annotate this, it is, let's see, this one's actually very easy to document here. This thing, m of I minus 1 j minus w of I is max value if we add this item to the knapsack. Because basically it's like, I gotta like break it down further. Weight of knapsack after adding this item. That's what that one is. Max value of remainder of knapsack is basically what this is. And this is value of this item. So that's what that whole thing represents. And then furthermore, this thing represents the max value without this item. So it's essentially the max value without this item, or it's do we include this item or not? That's basically all that we're doing when we look this up on this table. They, of course, are using super cryptic names and not leaving any comments to explain what this might be doing, so naturally. Now, what we see is that this is going to be 0 versus 4. We can put this item in the knapsack. Here, let me go back to Wikipedia. We can include this. If we don't include this item in the knapsack, then the value is 0. Obviously. If we do include this item in the knapsack, then this value is 0. That was the previous best value for that weight, plus 4, or plus 5, the current value of this item. So 5. For this space, we'll do the same thing. That would point back at that. Again, just subtracting 4 from the weight because that's the current value of this thing. So we still get 5. And likewise for 6. Because that's going to be the same process in all of that. So this agrees with the example picture so far. Then we repeat the process for the next item. So now we're saying, okay, what if this item, what if we look at the amounts for item 2 here with a weight of 3 and a value of 4? Well, again, it's going to be, if it doesn't fit here, then we just look at the previous value. We can't include this item in the knapsack. Therefore, the best we can do is whatever we got from including value 4. Or from including item 1. Same here, same exact thing. Then for this one, this is the one where we can actually fit it. So this one, since it has a weight of 3, you know, the value, the maximum value without this item, but with the same weight, is the 0 immediately above us. And if we subtract our weight of 3, that's still a 0, and so our computed value here ends up being our total value for this item of 4. It's going to be the same here. No, it's not. No, it's not, because what we're going to see now is we could either not include this item in the knapsack, in which case the remainder of our calculations tells us we'd get a value of 5. Or we could include this item in the knapsack, and then the remaining 1 unit of weight in the pack, the best we could do is a value of 0. Now, the plus our value of 4, that means our total value there would be 4. But 5 is better, so it would be better to leave this one out and just go with the previous item. Same deal here. Same deal here. Does this agree? It does. Okay, so I think I'm understanding the problem now. This doesn't even necessarily directly help me solve the actual advent of code problem, but I need to understand this technique. Okay, next item. This has a weight of 2 and a value of 3. Now, same deal here. It's just going to be 0. You can't actually do any better with that. Now, right here, the previous value is 2, and the other best is 0. So this is where we can include this item in the pack, and we'll get our 3 value out of it. Now here, it's going to be 3 versus 4, so this is again going to be 4. Here, we're going to have an even more dramatic result because if we don't include it, we can actually get a value of 5 in there. If we do include it, then it would be just 3, so we'd get all the way up to 5. But then much more interestingly, this is where we actually start to see something fun coming out of this problem. So there are two possibilities here. If we don't include the item in this space, then the best that we could do is 5. A value of 5 from putting this item into the pack. So that's our best value if we don't include this. But if we do include this, then that would be looking back at this one and saying, okay, so we include this for a weight of 2. Then if we look at our previous best for the remaining weight of 3, that's 4. So that means that we actually have our previous of 4 plus our value of 3, and that's equal to 7, actually, is the best that we could get here. And this should make some intuitive sense, right? We could spend our 5 weight on just one item here with a weight of 4 and a value of 5. We could do that, or we could spend our 5 weight on these 2 items with values of 4 and 3, and that gets us a total value of 7, which is better. So 7. And then, better yet, for this one, it would actually be 5 plus 3 or 8 for that. That would be the overruling value there. Still agreeing with the example on Wikipedia. One more run of the algorithm, and I'm not going to annotate it so heavily. Let's see, this one would actually fit. So this would have a value of 2. This one would be the max of 0 plus 2 or 3, which is 3. This would be the max of 3 plus 2 or 4, which is 5. This would be 4 plus 2 or 5, which is 6. This would be 5 plus 2 or 7, which is 7 either way that you shake it. And then 7 plus 2 or 8, which is 9. So what I'm not really understanding then is why this example then does this. It like highlights a few more things. Oh, I see. So what they're saying now is that in order to figure out, so this is, 9 is the maximum value of items that you can have in the knapsack. And the way that you would figure out which specific items those are is by saying, okay, so we know that the bottom right corner of our table here is the maximum value. But if that is our maximum value, so that means that we do have item 1. That has a weight of 1, which scoots us back to this column. So then we're looking at this, I think. This has a weight of 2, so that kicks us back to there, which gets us to that. I'm a little confused by that because what happens if one of those items like wasn't included? Okay, well at least I sort of get it, and I don't actually care about solving that problem like to that extent. So, okay, I see how this would kind of work. Now here's the problem. I have a bad variant of the knapsack problem where the values are constantly changing. So how would I do this? If I go back to our actual advent of code problem here, I have something worse than this, which is frustrating. Because I have this, like, situation where the time that I take to go somewhere also affects the outcome here. It's not just a matter of picking arbitrary things. It's like my choice of the order that I go through these things also actually makes it affects the result of the problem. I'm really stumped, to be honest. The only way that I can think to do this is the, like, terrible recursive factorial way, which, I mean, I can just do that in JavaScript easy. Like, zero problem, won't take me any time, but wait, why did it put it there? Gosh dang it. Get out of here, dude. Just drop it into the downloads folder. Thank you. Okay. What's my program input? Regex magic. Now, how do you do regular expression matches in JavaScript again? I need to extract groups. Yeah, there we go. It is string.match. Okay, so let's see, that would be name flow rate. And then, oh no. How would that evaluate? We'll do that. Aim, flow rate, and others. And others is equal to others dot split on comma space. And that should give me what I want. That doesn't work. Oh, crying out loud. Fix all the stupid problems. My regex did not match this line. It matched all the other lines, which is fascinating. Except not really. I don't know why. Yeah, no, it totally didn't actually work. Okay, let's go into debugX and figure out what I'm doing wrong. What is wrong with you? This totally should recognize, because when I come in here, does that work? I mean, like, can I just flip that around? Get out of here. Come on. This works fine. This works fine. What is wrong with you? Is it really just... It's really just greedy quantifier nonsense again, as always, as it always is? Why are you not repeating this group? It leads right into this. What? Why are regular expressions this way? Why are they this way? It doesn't make any sense. Why should that be the only thing that gets captured? Like, what? Like, is this the problem? Oh my goodness. Group capture nonsense sucks so bad in regular expressions. It sucks so bad. And it still doesn't even work on this line for some reason. Despite the fact that it's like clearly identical to the same, like... Oh, wow. There can be only one valve, so then it, like, you need to be able to skip the... I'm sorry, that even that doesn't fix it? Hilarious. Make the S optional on every word. I love that. Okay, there we go. I've got my data finally. So, oh my goodness, I'm so toast tonight. I've been doing this challenge too many days in a row. For real, I'm not sure that I can do this tonight. This sucks. Yeah, I quit. I'm sorry. I'm sorry. This is beyond me. I like the reason I'm doing this challenge is to figure out how to do interesting things in dreams, but I literally don't know how to solve this problem at all. Much less how to do it in dreams. I'm not up for this on a Sunday night. I'm sorry. I'll ask around about how to actually solve this problem. And then maybe tomorrow I can come back and actually solve it in dreams. Because it's just not happening. I'm sorry. So I'm going to call it. Bye.